In this video, we're going to talk about angles and their measure. We're going to convert between degrees, minutes, seconds to the decimal degrees and back again. We're going to draw angles in standard position. We're going to convert between degrees and radians. We're going to find coterminal angles. We're also going to find reference angles, although it's not listed there as one of our outcomes. We're going to find the length of a circular arc, and then we're also going to find the area of a sector. And again, that's not listed, but we are going to cover that in this video. We're going to use linear and angular speeds to describe motion on a circular path as well. So let's begin with what is the measure of an angle. So we're going to use, by default, we're going to use Greek letters, and this is alpha. And it's usually denoted when we're talking about the measure of an angle is m and then the angle that we're measuring. So m and then in parentheses alpha, the angle alpha. And it is the amount of rotation from the terminal side, or from the initial side where we start, to the terminal side. And we usually use rays. So we'll use not a line segment or a line, but actually rays, where we have a beginning and then it goes on forever. And where two rays come together is what we call the vertex of the angle. Now, the way in which we find this rotation, how far did it rotate, the angle measure, is we take a circle and we take the circle, the circumference of the circle, if you will, and divide it into 360 equal arcs. So in other words, when we're talking about an arc of a circle, so here's my circle and here's my center, and I'm going to cut it so that each one of these arcs, that's this length of the circle, so it's a piece of the circumference, is equal to 1 degree, because we're going to take our circle and divide it into 360 equal arcs. Now, obviously, this is not drawn to scale. This is not going to give me 360 equal arcs. So that's where the degree, 1 degree, comes from. And typically, like I said, we're going to use Greek letters to label our angles. So the ones that we're going to see is theta. So it looks like this, looks like a zero with a bar through the middle. We call that theta. We're going to call this phi, and it can look like this, or it could look like this. If I'm being real fancy, I'll try this one, but more often than not, I'm going to do that one. Alpha, this one we talked about before, beta, and then gamma, which I don't know, kind of looks like, I don't know, like an R, a fancy R, if you kind of squint at it. So then here's our definition. Here's our formal definition. The degree measure of an angle is the number of degree in the intercepted arc of the circle centered at the vertex. And 1 degree is 1 over 360 of a circular rotation. So that goes back to my picture up here, which was when we're talking about the angle measure of this, how many of those 1 over 360ths do I end up with to get this measure? How far did I rotate? Now, when we're talking about an angle in standard position, that means that my initial side is right here at positive x-axis. So it's right here at positive x-axis. And then for a positive rotation, we actually rotate in the counterclockwise. A negative rotation, when we go in the clockwise rotation, that is now a measure that is a negative angle. So positive angles will rotate counterclockwise, negative angles will rotate clockwise. We also like to talk about quadrants. When we're talking about the measure of an angle, we like to think about the quadrants they're in. Because when we get into further, like sine and cosine, which are our ratios, we like to know where we are. So when my x and my y are both positive, then we're in quadrant number 1. And again, we're going to label our quadrants going in the counterclockwise direction. In quadrant number 2, my x is negative and my y is positive. And in quadrant number 3, I have a positive, they're both negative x and a negative y. And then down in quadrant number 4, I'm going to have a positive x and a negative y. And this is going to be really important in our next video. So we want to determine where each angle lies. Now, when we break up our quadrants, we're going to break it up so that a quarter of a turn, a quarter of a rotation around the circle is 90 degrees, because that is 360 divided by 4 gives us 90 degrees. So that's a quarter turn. If we have done a half of a turn, that's 180 degrees. And if we've gone 3/4 of a turn, we've gone 270 degrees. And if we do a 1 full rotation, we get 360 degrees. Now notice that 0 and 360 degrees lands in the same position. If I would like to know where each one of these angles lies in terms of quadrants, I need to think about how far do I rotate. So 85 is less than 90. So if I go back up here and I can see that 85 as a number is less than 90. So 85 is less than 90. So it is in this quadrant, because in this quadrant, it's going to be the angles not inclusive of 0, going all the way up to 90. So in quadrant number 1, you're going to see me do it. Note this is Q1. This is going to be from 0, my angle, to 90 degrees, non-inclusive. Quadrant number 2 is going to be from 90 to my angle alpha and less than 180 degrees. Quadrant number 3 is going to be 180 degrees, less than alpha, less than 270 degrees. And then my last quadrant is going to be, so Q4 is going to be 270 degrees, which is less than alpha, which is less than 360 degrees. So we can clearly see that 85 is between 0 and 90. So this is in quadrant 1. So that's where that one lies. Now this is a negative 200. So if we were to go backwards in this direction, this is a negative 90 degrees. This is a negative 80 degrees. And then this becomes a negative 270 degrees. And lastly, going backwards, this is a negative 360 degrees. So 200 is between 180 and 270. It's a negative 200. So going in the backwards direction, I'm going to go to a negative 180 to a negative 270. So I actually land in quadrant number 2. Now, I have 1568. Well, if I were to draw 1568, I'm going to go in the positive direction. 1 full rotation is 360. So I've done at least 1 full rotation. So I have 1568, and I'm going to subtract off from that 360. So if I take 1568 and I subtract off 360 degrees, I still have 1208 degrees. And I still don't know where I land. So I'm going to do another full rotation. So I'm going to take that 1208. I'm going to subtract off another 360 degrees. So 1208 minus another 800, or not 800, that's my answer, minus another 360 degrees is going to give me 848 degrees. Well, that's still bigger than 360, so let's do another rotation. So I'm going to go rotate again, and so I'm going to take that 848, subtract another 360, and I get 488. So I have 488 is my answer. So 848 minus 360 is going to be 488. Still bigger than I want. So I'm going to rotate around one more time. Then where am I? Well, I'm going to take that 488. I'm going to subtract off another 360 and see where I'm landing. So I'm going to subtract off another 360, and I get 128. Okay. So where do I land? Well, this is at the 0 mark again. This is at the 90, and so it's going to land somewhere in here. So I have done my first rotation, my second rotation, my third rotation, my fourth rotation. I have taken off 4 rotations so I can figure out where I really land. And so I land for this one 128, which is in quadrant number 2. And we're going to actually talk about this. It's called a coterminal angle, and we're going to talk more about this later in the video. There are certain types of angles that we are going to be looking at, and here's some new vocabulary potentially for you. The first one is an acute angle. This is an angle that is less than 90 degrees. And then, of course, if you've taken high school geometry, you have heard of right angles. Right angles are worth 90 degrees. Obtuse are angles between 120 degrees. Obtuse angles are bigger than 90 and less than 180. And then, of course, the straight line, which is 180. Quadrantal angles is something else we're going to talk about, and it's a quadrantal angle anytime I land on an axis. So a right angle, a straight line, the 270, and the 360 are all considered quadrantal angles because they land on an axis. Now, if you take pictures on your phone or anything that connects to the internet, it's going to tell you exactly where you had that picture taken, unless, of course, you remove that feature. And what I mean by that is it's going to give you your longitude and latitude in degrees, minutes, and seconds. Because if you think about the Earth, if you only did it in degrees, if you look at a globe that has all of your longitude and latitude marks on it. So here's all your longitude and latitude marks, right? Each one of these points is where degrees are. But if you're standing right here, if you give it in terms of only degrees, you're going to be way off of where you actually are. So to get a little more precise, we use degrees, minutes, and seconds when we're talking about the angle measure. Now, when we talk about the degrees, minutes, seconds, it's just like in units of time. 1 degree or 1 hour equals 60 minutes. 1 minute is equal to 60 seconds. So this is going to allow us to convert anytime we have a decimal like this into degrees, minutes, and seconds, like we do here. So if I need to convert from degrees, minutes, and seconds into decimal degrees, then I first start with the 6-minute mark. Now I have this unity fraction, 1 degree over 60 minutes, or 60 minutes over 1 degree. It just depends on which way I'm converting. Similarly, I have 1 minute over 60 seconds, that's 2 tick marks, or I have 60 seconds over 1 minute. Now, I don't have to convert the 45 because the 45 is already in degrees. What I need to convert is the 6 minutes. So I put 6 minutes over 1. Now I need to choose the correct unity fraction here or here that is going to give me an answer in terms of degrees. So in other words, this minute mark needs to cancel out with my unity fraction. So I need it to be diagonal or in numerator and denominators when I do this multiplication of the unity fraction. So I'm going to multiply by 1 degree over 60 minutes. So I will end up with this unit and this unit canceling. So I end up with 6 over 60 or 1 over 10 or 0.1. So that tells me that 6 minutes is equal to 0.1 degree. So to convert this into a decimal, this is 45.1 degrees. Now, as with our units of time, then I know I can also do this 1 degree over 3,600 seconds, or 3,600 seconds over 1 degree. So that's like our unit of time, right? So 1 hour is 3,600 seconds. So it's something similar to that. Now I'm going to do my second conversion here. As before, I'm going to start with the 19. So I have 19 minutes over 1. My unity fraction, because I want to eliminate the minute unit and I want to end in degrees, will be 1 degree over 60 minutes. And that'll allow me to cancel those. And I'll end up with 19 over 60 degrees. I can take my 22 seconds and convert first into minutes and then into degrees, or using these unity fractions, I can go right into degrees. So that's what I'm going to do. So for the second part, the 22 seconds, I'm going to put it over 1, and its unity fraction, because I'm going to want to eliminate and go into degrees, is going to be 1 degree over 3,600 seconds. And so I end up again, my seconds will eliminate, and I have 22 over 3,600. Now, what's happened is I have, give me a moment, there we go. I have 44 degrees, 19 minutes, 22 seconds is equal to 44 degrees plus the 19 over 60 degrees plus the 22 over 3,600 degrees. So I'm going to get my calculator out, and then I'm just going to add up all of these numbers, and that's going to tell me what it is in terms of degrees. I'm going to put that in my calculator. I'm going to get 44.3227 and a bunch of sevens repeating. So, and that's in degrees. Now, personally, I kind of feel like it looks better this way than this way. But there's going to be times in which you're going to use one or the other. Now let's convert the other way. With our problem A and B up above in my previous example, I was able to just convert the degrees initially by itself and the minutes, or not the minute, the degrees, the seconds and the minutes individually. This is going to be a multi-step process. So the first thing I'm going to do is only worry about the decimal degree. So I don't worry about the 39, so I'm going to take 0.25 degrees over 1. Now this time I want the degrees as units to cancel. So my unity fraction is going to be 60 minutes over 1 degree. So once again, I'm going to get my calculator out. My degrees will cancel, my unit degrees will cancel. So I have 0.25 times 60. And I get 15 minutes. So 39.25 degrees is the same thing as 39 degrees and 15 minutes. And that's it. Now let's take a look at my next example here. So I have a negative 122.786 degrees. As before, I'm really only going to focus in on the decimal part because 122, the negative 122 is already in degrees, so that's okay. So 122 degrees. So when I take the 0.786 degrees over 1, my unity fraction is going to be 60 minutes over 1 degree. Again, what will happen is that my degrees will cancel. And now what I've got is I've got 47.16 minute. So this is 47.16 minute. But because of the fact I still have a decimal here, I am going to do another conversion. And I'm going to do this until I don't have a decimal or until I need to round to my second mark. So I have a negative 122 degrees, 47 minutes. I'm going to come over here and I'm going to do 0.16 minute over 1. And now my unity fraction is 60 seconds over 1 minute. And this will allow these units to cancel. I'm going to get my calculator out again, and so I'm going to do 0.16 times 60. And I get 9.6. And at this point in seconds, and at this point I usually round, but I may leave it as 9.6 seconds In this case, I'm going to go ahead and round. And so I'm going to round this to its nearest integer, which is 10 seconds. And there is what a negative 122.786 degrees is in terms of degrees, minutes, and seconds. When we are adding degrees, minutes, and seconds, we need to add the degrees together, we need to add the minutes together, and we need to add the seconds together. So the first thing I'm going to do is add my seconds. So I have 52 seconds plus 28 seconds. And that gives me 80 seconds. But 80 seconds is the same thing as 1 minute plus 20 seconds. Because remember, 80 seconds is 60 seconds plus 20 seconds, where 60 seconds is 1 minute. So that tells me that I need to make sure that when I'm doing my minutes here, which is the 55 plus 22, I need to add that 1 right here onto that. Or I could do this all at the end. I just like to do it as I go. So once again, I'm going to do, and this is my minutes. I'm going to add all these together. So I have the 55 plus 22 plus 1 more. That gives me 78. This is 78 minutes, which is the same thing as 60 minutes plus 18 minutes, which is the same thing as 1 degree plus 18 minutes. So that tells me when I do my degrees here, it's going to be 7 plus 8 plus 1 degree because of this 1 degree. So my answer is 16 degrees. Now I need to pull all this together. When I'm done, I'm going to get the 16 degrees, and that comes from here. I'm going to get the 18 seconds, that comes from here, so 18 seconds. And then I have the 18 minutes, and then the 20 seconds last. So my final answer is going to be 16 degrees, 18 minutes, and 20 seconds. Now I'm going to go ahead and do the multiplication. So I'm going to multiply 4 all the way through. I'm going to multiply each one. So I multiply the 4 through, and I'm going to get 36 degrees. That's the first part. So 4 times the 9 degrees. Then I'm going to take the 36 degrees, and I'm going to multiply it by 4, and so I get 144 minutes. And then I'm going to do the 4 times the 12 seconds, and that will give me 48 seconds. Now the 48 seconds is less than 60, so that can stay exactly how it is. However, we know 144, so 144 minutes is the same thing as 2 times 60 minutes plus 24 minutes. So we know that this is 2 degrees. So that 2 degrees needs to be added there. So this is going to be equal to 36 degrees, 24 minutes, and 48 seconds. And I just talked about it, and I forgot to add those 2 degrees there. So it'll be 38 degrees, 24 minutes, and 48 seconds. Now let's look at our last example here. And with our last example, we have to borrow, because what I'm trying to do is I'm trying to take 6 minutes and subtract off 54 minutes. Clearly, I can't do that because I'll get a negative number. However, 76 degrees is the same thing as 75 degrees plus 1 degree, which is the same thing as 75 degrees plus 60 minutes. So that tells me I can write 76 degrees 6 minutes as 75 degrees and 66 minutes. Then I can subtract off the 18 degrees and 54 minutes. And I end up with 57 degrees and 22 minutes. So just like when we're doing numeric values, if I'm doing a subtraction and I'm trying to take 7 away from a smaller number. Either I need to go negative or it needs to be borrowed if I'm doing something that looks like this. So if I have 360, I'm subtracting off 21. I have to, quote, borrow from the tens, and that's what I have to do here when I'm trying to do 6 minutes, subtract 54 minutes. Clearly, I'm not going to have a negative number there because I can borrow from this. Now, it's not always true. If this would have been 5 degrees, then I still would have had to borrow, but I'm just going to end up with a negative number, a negative rotation, if you will, when I get done. Now we need to talk about radians. When we get into calculus, and that's what this class does, is a prep to calculus, so it's called pre-calculus, 99.9% of the time we're in radians. We're not in degrees. So we need to talk about what a radian is and how do I convert from degrees to radians or radians into degrees. So here's what the official definition is. 1 radian is the measurement of the central angle of a circle, the length of the arc between the initial side and the terminal side to the radius of the circle. 1 full revolution equals 2 pi radians and blah, 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 blah. And you're like, what just happened? Well, basically, if we were sitting on the unit circle, and what a unit circle is it's a circle centered at the origin with a radius of 1. Therefore, unit circle. Now, we know the circumference of a circle is 2 pi r. That tells me if my radius is 1, my circumference is equal to 2 pi times 1. In other words, 2 pi. And that's where that comes from. That's where that whole 2 pi up there came from, is it comes from here, really. If I then take this 2 pi and divide it up here, if 1 full rotation is 2 pi, then that tells me that this arc length must be a quarter of that, or in other words, pi over 2. This arc length, again, because remember we're talking about a circumference, must be pi, and this arc length must be 3 pi over 2, and the full arc length is 2 pi. So when we are doing our degree measurement, remember it is the arc length. We're talking about how far did I rotate, which is the arc length when we're looking at a circle whose vertex is centered at the center of the circle. So that tells me that I get a really nice conversion, and the conversion that I can use is multitudes of them, but the nicest one is 180 degrees. Remember, this was the same thing as 180 degrees is equal to pi radians. Now, make sure that you pay attention that because we're talking about a rotation, it is radians, not just pi. Pi is 3.14-ish. But when we're talking about an angle measurement, we talk about radians. The other one I could use, it's not wrong to use, is 360 degrees equals 2 pi radians. You can use either one. By convention, we usually do 180 degrees equals pi radians. The unity fraction that we use is either 180 degrees over pi radians, RAD, or pi radians over 180 degrees. And I'm going to be honest with you. The further and further I go with my videos and all of this, I have a tendency to be a little lazy and I drop off the radians. But really, when I see 180 degrees over pi, it is pi radians. Or somebody forgot, it depends on who's doing it, forgot to just, or got lazy, like myself, and drop the radians part. But they are, when you see 180 over 180 degrees over pi, it should be pi radians because it is an angle measurement. And in fact, look at this. I have 2 pi, but I'm not putting the RAD next to it. But it does say convert each radian measurement, so it's assuming RAD is next to it. So because of the fact that I am now asked to convert, because I'm going to spend most of my calculus life in radians, I'm going to take my 360 degrees, and again, I want to cancel my degrees. So I'm going to put this over 1. My unity fraction is going to be pi radians over 180 degrees because that will allow my degrees to cancel, and then I'll end up with a radian measure. Now 30 goes into 30 once, 30 goes into 186 times, so my final answer is pi over 6, and I really should put radians next to it. So 30 degrees is equivalent to pi over 6 radians. And 225 degrees over 1, my unity fraction is pi radians over 180 degrees, and this will allow my degrees to cancel, and I end up with 5 pi over 6 radians, and that's with the cancellations here. Lastly, I have a negative 48 degrees over 1. I want to cancel my degrees, so I'm going to put pi radians over 180 degrees. This will allow my unit of degrees to cancel, and I end up with, I'm going to take 100, I'm going to take 48 divided by, let me see, I'll start with 4. 180 divided by 4. I can do something higher, so I'll do 180 divided by 12, and 48 divided by 12, and we get 4 over 15. So 4 pi over 15 radians is what it reduces to. It is always assumed that we are going to reduce, and not drop that negative sign. It's assumed we're always going to reduce, so that's what you will do when you have it in radians, is reduce. It is ideal to leave exact, so I want to talk about that too. This is exact, this is exact, this is exact. Now, if I get my calculator out and I use my pi button and I divide by 6, the answer I get, well, it's an equivalent, it's a decimal approximation. The decimal approximation is 0.52359877756 radians. It is preferable to stay with the exact pi over 6 radians versus the decimal approximation. So as a heads up, you're going to see almost everything on the homework and quizzes and absolutely on the test is going to ask for exact. So you want to use the exact. Now what we're going to do is we're going to convert from radians into degrees. Now remember, there is an RAD here. It's just implied because they're telling us we're in radian measure and we're going into degree. So that is implied, but I am still going to write it here anyway. So this is going to be RAD right here. In this case, I want to get rid of my radians. So I'm going to put pi radians here and 180 degrees there. This will allow my radians to cancel and my pi's will cancel. And 2 will go into 180, 90 degree times. Similarly, I'm going to do the same thing here. This is a radian, and I'm going to multiply by 180 degrees over pi radians. My degrees and my radians will cancel, and I end up with 255 degrees. Negative 7 pi radians. I'm going to multiply by 180 degrees over pi radians. Again, my pi radians and my pi radians cancel. And I end up with just, don't forget the negative like I did before. So I'm going to get a negative 7 times 180, which gives me a negative 1260 degrees. Now I want to talk a little bit, I know we haven't, there isn't any examples here, and you might see this on the homework, and it's going to ask you to convert radian measures that are not nice. So say it's asking you for 2.163 radians, and they want us to convert into degrees. Now in this case, I'm not going to get an exact value. I'm just not going to get an exact value, but I'm still going to set it up the same way. 2.163 radians over 1 multiplied by 180 degrees over pi radians. And this is where I will need to use my calculator, and I'll need to use my pi button. So what I would put in my calculator is 2.163. I would multiply that by 180 and then divide that answer by pi using my pi button, or 3.14, whatever it is that's being asked to use. And then because I'm going to get 123.9307711 degrees, and it actually goes further than that. It's going to continue, but that's as far as my calculator goes. So this is actually a decimal equivalent. You would then at that point round to whatever it is that they're asking you to round to, like the nearest decimal degree. And so you would say this is equivalent to 123.9 degrees. Just as something to think about when you are doing your conversions, if you don't have a nice radian measure to begin with. You end up with like a decimal 2.163 or something like that. Just a heads up. Okay, the next thing we're going to talk about, and this is a long video, the next thing we're going to talk about is coterminal angles. Now remember my example up above where I had 15 or 1623 degrees, and I said, where did we land? Well, I don't know. I didn't know until I started doing the rotations. What I can do, rather than doing the drawings of the rotations, which is not wrong, right? So we have our first rotation, and then we have our second rotation, and then we have our third rotation, is I can find its coterminal angle by adding or subtracting multiples of either 360 degrees if I'm in radians or degrees, or 2 pi k if I'm in radians. And if they start and end in the same place, if they have the same initial side and the same terminal side, then we say those two angles are coterminal. So I'm going to take my 1623, and I'm going to find a coterminal angle. So that means I'm going to pull off a multiple of 360 degrees. So I can do it one at a time, but I'm not inclined to do that. So if I take 360 and I just guess and I say 4 is a nice number, that gives me 1440. So I think I might do this by pulling off 4 multiples of 360. And I still might not have the coterminal angle that I want. So let's go ahead and just do that. So 1623 minus 360 times 4. And so I get 183 degrees. So 1623 degrees is coterminal to 183 degrees. That should be 183, not 180. 183 degrees. Now, if I would have chose 4 rotations, so 1623 minus 360, I'm going to subtract off 5 rotations. So again, I'm going to take 1623 minus 5 times 360, and I get a negative 177 degrees. These are also coterminal. They start and end in the same place. So coterminal angles are 360 degrees apart from each other, or 2 pi radians, if we're in radians, apart from each other. So we want to find the degree measure of 2 positive and 2 negative angles that are coterminal to the given angle. To find my first positive coterminal angle, I'm going to take 45 degrees and I'm going to add 360 to it. This will give me my first positive. I'm going to take 45 degrees, I'm going to add 2 times 360 degrees, which is going to give me my second positive one. Similarly, I'm going to take 45 degrees, I'm going to subtract off 360 degrees, will give me my first negative, and 450 minus 2 times 360 is going to give me my second negative coterminal angle. And I'm going to do the same thing for B and C, so I'll let you do those. If I'm trying to determine whether or not they're coterminal or not, all I'm going to do is see if I add or subtract multiples of 360 if I'm going to get the other answer. So if I take 20 degrees and get 300 and add 360 to it, do I get 380 degrees? So 20 plus 360 does indeed, so this is yes. 8 degrees, and then notice this is a negative angle, so I'm going to subtract off 360 degrees. So I have 8 minus 360 degrees, and it is negative 352. This is not this number, so the answer is no. Remember, coterminal angles have to be 360 degrees or 2 pi away from each other, or multiples thereof. So I have negative 128 degrees. I'm going to add to it multiples of 360. I'm thinking maybe 2. So 2 times 360. And so I have negative 128 plus 2 times 360 in my calculator, and I get 592. And so yes, these match. So the answer is yes. So that's all it means. Coterminal means that I start and end in the same place. So here's my 45 degrees. Here's my 45 degrees. If I do from this, starting here, one full rotation, 360 plus another 45, that is coterminal, as if I would have started here and gone a negative rotation, and that is also coterminal. Those two angles, the one in blue and the one in red, are coterminal to that angle that is in black. They start and end in the same place. Another thing that we pick up here is a reference angle. A reference angle. So what a reference angle is the shortest rotational distance from the terminal side back to the x-axis. And because it's a distance, reference angles are always positive, no matter which way you're rotating, because it is the shortest rotational distance to the x-axis. So you're going to sometimes see this as the reference angle as theta prime. I think in our book we use t prime, and that just means I am looking for the reference angle. So if I'm in quadrant 1, and my angle that I'm looking at is less than 90 degrees, my reference angle and my angle is the same thing, because the shortest distance back is exactly where I start. Now, the shortest distance to the x-axis, it doesn't have to be positive or negative, it's just the x-axis, would be this distance if I'm in quadrant number 2. So I can find that by doing my reference angle as being 180 or pi minus the angle that I'm looking at. If I'm down in quadrant number 3, the shortest distance is back to the negative x-axis, and that's why it is going to be my reference angle is going to be my angle, which is bigger than 180 degrees, or pi, and subtracting off pi, or 180 degrees. Lastly, if I'm in quadrant number 4, my reference angle is the shortest distance to the positive x-axis in this case, and the way I find that is the 2 pi minus my angle, or 360 minus my angle. Now, for an angle theta in standard position that is not a quadrantal angle, my sine, which we're going to talk about in the next video, of my angle theta is either going to be positive or negative of the sine of my reference angle. I'm going to talk about this in the next video, but this is just a heads up. So if I'm asked to find the reference angle in degrees and radians, we'll do this one in degrees and we'll do this one in radians. First thing is I got to figure out where 360 degrees is. Well, 360 degrees is somewhere down here. It's bigger than 270, but less than 360. My reference angle is this distance I need to travel. So I'm going to take 360 minus 330, and that's going to give me 30 degrees, and that is my reference angle, because that's how much further I need to rotate to get to the x-axis. 7 pi over 6. Well, now remember, this is pi over 2, this is pi, this is 3 pi over 2, and then we're back to 2 pi, and also 0. So 3 pi over 2, ignoring the pi, is 1.5. 7 over 6 is 1 1/6. So that's clearly less than 1.5. So I am down here somewhere. So here is my angle. My reference angle, because I need to go backwards. I need to go back to the x-axis. My reference angle is going to be 7 7 pi over 6 minus pi. So I need to take off that pi. I need to go back to the negative x-axis. So I'm going to make sure I have the same common denominator, minus 6 pi over 6. So my reference angle is pi over 6. This is pi over 6. Just like this was 30 degrees. Now, last one on this one. I have negative 3 pi over 4. Going back in the negative, this is negative pi over 2. This is negative pi. This is negative 3 pi over 2. And this is negative pi, 2 pi and 0. 3/4 is bigger than a half. Again, I'm kind of ignoring the pi part. So 3 over 4, that's 3/4. It's bigger than a half, but less than 1. So that tells me I am landing down here. And then it's a matter of how much further do I need to travel to the x-axis. Now we have a formula that says, hey, I'm taking my angle and I am going to subtract it from 360 or pi or whatever it is that I'm asked to do. Now remember, this is a negative angle. So if I were to say, oh, I need to go to, using my formula that is pi minus my angle theta, if this is theta, then I'm going to be doing pi minus a minus number. And that's going to give me a number that is not a reference angle. So do pay attention to your negative. Instead of doing pi minus theta, do pi plus my theta because my angle is negative. So I'd have pi plus the negative 3 pi over 4. And so my reference angle is pi over 4. So this is pi over 4. So be paying attention to your angles. And here's a little tip. Here's your tip. Reference angles are always less than 90 degrees or pi over 2. This is always true. So if you come up with a reference angle that is bigger than pi over 2 or bigger than 90 degrees, if you're in degrees, you made a mistake somewhere because they're always less than 90 degrees or pi over 2. I know this is a long video and I'm still not done. Now let's talk about the arc length of a circle. Now we talked about it before in the fact that if I'm at a unit circle, I know my full rotation is going to be 2 pi r. If it's on the unit circle, it's just 2 pi. What happens if I don't have a unit circle? Can I still find the arc length? And the answer is yes. This is the formula for the arc length. S is the arc length, alpha is the angle, and r is your radius. Now here's the thing. This is really, 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 really important. You have to be in radians. If you are not in radians, you're going to have to convert your angle into radians so you can actually find the arc length because you have to be in radians. So let's take a look at our first example. I have alpha is equal to 1 radian and my r is equal to 4 centimeters. They're asking for my arc length, and I need to make my s as a cursive because otherwise my s looks like 5s. So s is equal to my angle, 1 radian, multiplied by 4 centimeters. And my final answer is just 4 centimeters. I'm on the unit circle. If we take a look at our second example here, I have 60 degrees. Remember what I said up here? Up here, up here, still up here. I'm looking up here. I need to be in radians. So the first thing I have to do is I have to take my 60 degrees over 1 and multiply by its unity fraction. I need to multiply by pi radians over 180 degrees. That way these will cancel, and I end up with pi over 3 radians. Then my arc length is going to be pi over 3 radians, pi over 3 radians, multiplied by 2 meters, and my final answer is 2 pi over 3 meters. And you're thinking, what happened to my radians? Well, when we are looking at the arc length, because of this relationship, this relationship tells me that my angle of rotation has a relationship directly related to the arc length. So when I take my angle of rotation and multiply it by my r, I no longer have to worry about the radians part because that is the relationship that I have, and I don't have to have the radians part anymore. More on that later. The area of a circle, and again, pay attention right here. Bam, bam, radians. Almost everything we do is in radians. So now is the time to become really, really good at converting or being able to read a unit circle or something like that, because everything's almost always in radians. The area of the sector, the piece of the pie, the piece of the cake, the surface area, the top of the cake, the top of your pie, the top of your piece of pizza, is this equation. 1/2 my angle in radians r squared, or alpha r squared divided by 2. If I am asked to find the area of the sector, remember, you have to be in radians. So this is going to be equal to, the area is going to be equal to, first thing I'm going to do is 30 degrees over 1 times pi radians divided by 180 degrees. This is going to give me pi over 6 radians. So my area is going to be equal to pi over 6 multiplied by 6, the quantity squared, divided by 2. I should have some units on here, so let's call this 6 inches. So I'm going to have pi over 6 times 36 divided by 2, which gives me, I'm going to reduce this way, which gives me pi, or 6 pi divided by 2. These reduce, which gives me just 3 pi, and don't forget my units when I get totally done. This is area, so it'll be inches squared. If I don't have units, I'm going to write units squared, but that is my final answer. Now, preferred exact, but you could put that pi in your calculator and get a decimal approximation. Now, if we take a look at B, it is already in radians. So for B, my area is my pi over 12 multiplied by 8 squared divided by 2. Let's make this feet. So it's 8 feet. So I'm going to have pi over 12 multiplied by 64 divided by 2. So 4 will go in here 3 times. 4 will go in here 16 times. So I end up with 16 pi divided by 3. Now remember, dividing by 1/2 or dividing by 2 is the same thing as multiplying by 1/2. So I can continue to cancel, and I end up with 8 pi over 3 units squared. But I think I said it was feet, so we're going to call this feet squared. All right. Here's an application. We're almost done, by the way. A central pivot irrigation system is watering a circular field with a radius of 150 feet. The system rotates 30 degrees in an hour. How much is actually watered, area-wise, in an hour? So I have my radius. Here's my radius. Here's my problem child. So I know from up above, 30 degrees is pi over 6. So 30 degrees is pi over 6. And then now it's just a matter of using the area, which is equal to my pi over 6 multiplied by 150 degrees. It's not 150. 150 feet squared divided by 2. Here's an example in which I will probably use my calculator. So I'm going to go ahead and do pi divided by 6 times 150 squared. And then I'm going to divide by 2. And I get, as an answer, 5,890 point, I'll do it to 1 decimal place, 0.5 feet squared. And I would round to whatever my decimal is, or I could have gave it as an exact, but in this case, if you tell somebody that you're going to water some number times pi over 2 feet squared, they're going to kind of look at you like, what? So 5,890.5 feet squared is probably a better choice for the answer. Not applications. If we get nice numbers, we're going to leave them as nice numbers in this example, but if it's an application, it would make more sense to do the decimal approximation. All right, so angular and linear velocity. To go from revolutions per minute to radians per minute, we have another conversion. These are all on your formula sheet, so don't panic. And it kind of makes sense. 1 pi radians is 1 full revolution, right? Because we talked about that before. If we're on the unit circle, I've gone 1 full revolution. So my circumference is 2 pi r. So in other words, if r is equal to 1, I've gone 2 pi. So 1 revolution is 2 pi radians. And that makes total sense. So if I want to go from RPMs, revolutions per minute, to radians per minute, then I only have one unity fraction I have to worry about. So 30 revolutions per minute multiplied by my unity fraction, which is 2 pi radians equals 1 revolution. Now, the reason I set it up this way is so that this revolution will cancel, and I end up with 2 times 30, which is 60 pi radians per minute. And that's all you have to do. This one's a little bit more involved because we have radians per hour, and I want to end up in revolutions per second. So I've got a couple of unit conversions that I have to do. So this number, notice, does not have pi. So somewhere embedded in there is a pi. So I have 3,000 radians over 1 hour. My first unity fraction is because I want to get rid of radians. I'm going to have 1 revolution is 2 pi radians. This will allow my radians to cancel. So I'm going to end up with revolutions. Now, I want to go from hours. I need to convert hours, and I need to end up in seconds. So I have another unity fraction I need to tack on here. 1 hour is equal to 3,600 seconds. This will allow this hour and this hour to cancel. So what I'm left with is 3,000 multiplied by 1 revolution. So I'm going to have 3,000 multiplied by 1 revolution. And then in the denominator, I'm going to have 1 and 2 pi and 360 seconds. So I'm going to have 1 times 2 pi times 3,600 seconds. So now I'm going to get my calculator out. And I get my units. I have the units I want, which is the revolutions per second. So that's looking good. And I end up with my final answer is going to be, and make sure you have parentheses in all the right places in your calculator, 0.132, I'll go out to 6 revolutions per second. And so that is my final answer. And here's my final answer up there. Okay, now, angular velocity. Angular velocity is how fast do you rotate, which is your angle alpha in radians, divided by some time unit. That is angular, or omega. This is an omega, looks like W. It is an omega, and that's it. A radar antenna makes 1 revolutions in 2 seconds. What is the angular velocity? 1 revolution means that 1 revolution is, remember, 2 pi radians. And this is going to give me my alpha. So I've done 1 full revolution, which is an angular 2 pi radians. If I want to know my omega, I take my alpha and divide by my time unit. So my alpha is 2 pi radians. my time unit is 2 seconds. And so I end up with pi radians per second. And that's my answer in angular velocity. That's how fast it is rotating. A windmill blade is 30 feet long and rotates 90 degrees for every 30 seconds. What is its radians per minute? And then what is its revolutions per minute? Now, we don't even care about the 30 feet long. That is not part of the conversation here. What we do care about is this 90 degrees. And 90 degrees, I'm going to have pi radians over 180 degrees is my first unity fraction because I have to be in radians. And I end up with pi over 2 radians. So pi over 2 radians. To do my angular velocity, this is going to be 90 degrees, which has to be pi over 2. So pi over 2 radians. Now, I have 30 seconds, so 30 seconds. However, I want radians per minute, so I have to tack on another unity fraction here because I need to get rid of the seconds. I need to end up in minutes. I want radians per minute. So 60 seconds is equal to 1 minute. This will allow me to get rid of my seconds and end in minutes. So my answer is going to be pi over 2 times the 60 divided by the 30, and then I end up with radians per minute. So you can see that this 2 and this 6 will cancel, giving me 30. This 30 and this 30 will cancel, and I end up with pi radians per minute. So that answers my radians per minute. Now I got pi radians per minute. I want to end up in revolutions per minute. So pi radians over 1 minute. Now we know that for one revolution is 2 pi radians. So there's my unity fraction. So my radians and my pi's cancel, leaving me 1 over 2 revolutions per minute, or 1/2 RPM. That looks like a minimum, and that should be minutes, M-I-N. Okay, now we also need to talk about linear velocity. If a point is in motion on the circle of a radius r through the angle alpha radians in time, then its linear velocity is given as v. V is used for linear velocity. Of the arc length divided by t. But arc length is just my angle multiplied by r, my angle in radians multiplied by r. So my velocity is my arc length divided by t, which is just alpha r divided by t, which is just r multiplied by alpha divided by t, which is just r times omega. Like, this is the best ever. If a windmill is 30 feet long and rotates 90 degrees every 30 seconds, what is the linear velocity in miles per hour? Now, we already did part of this. We already found up here, the linear or the angular velocity. We already found that. Remember, we found that to be pi over 2, what was it? Pi radians per minute. So we already found that. But now we need to have the length. So we know that our omega is pi radians per minute. Okay. Now remember, linear velocity is just angular velocity multiplied by my radius. So my velocity is pi radians per minute multiplied by my length, which is 30 feet over 1. Now that's it if I wanted it in feet per minute. However, I want it in miles per hour. So now I have to do all of my unity fractions to get all my units to align. So my first one is I'm going to take my minutes and convert into hours. So I have 60 minutes is 1 hour. That will eliminate my minutes. That will give me the hours that I need. The other unity fraction that I need is my feet. So for 1 mile, there's 5280 feet. That would eliminate my feet. Now remember, arc length no longer has the radians. So when you are doing this multiplication, the radians is no longer an angle measurement, it is an arc length measurement. So that means that that radian is no longer important here. So my answer is, in the numerator, I'm going to have a pi times a 30 times a 60 times a mile. So I have pi times 30 times 60 times the mile unit. In the denominator, I'm going to have 1 and 1 and 5280 and hour. So I'm going to have 5280 hour. I'm going to get my calculator out and I'm going to do 30 times 60 times pi. And I'm going to divide it by 5280. And I end up with 1.071 miles per hour. And you think, when we were up here before and you're thinking, oh, 30 times pi feet per minute, that's fast. But guess what? Even I can walk this fast. In fact, I walk about 3.5 miles an hour. So I can walk 3 times as fast as how fast this windmill is rotating in terms of linear velocity. And that's it for this video. Super long, lots of information in this section. Take copious notes and ask questions in class, and we'll see you in class.